Uh, so last time we were talking about electric field. So I'm going to continue on with that and talk about continuous distributions of charge. So things like lines of charge, surfaces of charge, spheres of charge, blobs of charge. Okay, we're going to see how to handle those kinds of things. So we said for a point charge, just to refresh your memory, that the electric field is equal to K times Q over R squared R hat. It's a vector, so if I write a vector on this side, I must have a vector on this side because I have an equal sign there. This is to remind me that the field of a point charge is radially symmetric. It's got spherical symmetry. It radiates out in 3 dimensions. If I draw a slice of it in 2 dimensions, for a positive bit of charge, the field lines begin on the positive charge, and they go out to infinity like this. Okay, so this is our little picture of the electric field. It's helpful, all right, I think. R hat is that little radial vector that tells me, okay, it's radiating outward everywhere. If it's a negative charge, it looks exactly the same except the field lines are pointed in the opposite direction. So for a negative charge, it's like this. It's exactly like the other one, except the field lines end. I guess end would be the right word. They end on the negative charge. Okay. R hat still points in the same direction, but since it's a negative Q, that turns all of the field lines this way. Okay, so this is a negative Q. Okay, this was a positive Q. Then we saw that, well, this is summable. It's a vector. So you take some distribution of point. Yes?
Would R hat on the negative be pointing inward too?
No. R hat, this is a good question. R hat still points in this direction, but E is equal to minus, well, let me write it like this. It's equal to K times a negative Q over R squared R hat. So that gives you a vector in the opposite direction of R hat. That's what you want. So we saw that this was summable. If you take a collection of point charges and you want to know the field at some place or point in space due to this collection of charge, you sum it up as vectors. All right? So we're going to extend that idea to a continuous distribution of charge. So let's say I have this blob of charge. I don't know, a dog bone or something of charge. I'm going to assume that it's uniformly distributed. The charge that it's distributed doesn't have to be. I'm going to assume that it's uniformly distributed over the dog bone and it's all positive. Okay? And I want to know, well, due to this blob of charge, what is E out here at this point? Well, I can get an approximation to it by breaking it up into little bits of charge and summing over all those little bits. That's what I'm going to do. I'm going to break it up into little cubes of charge. Okay, these seem like pretty big cubes, but I'm only going to draw 3, but I'm assuming that I'm covering the space, okay? So I'll call this delta Q1. This is delta, means a little bit of charge, delta Q2, and delta Q3. And those go on and on and on up to delta Qn, depending on however many I can fit into that blob of charge. For each one of these little Q or delta Qs, I've got an R1 hat. I'll try to get it to point. R2 hat and R3 hat. Okay? Those are those little vectors pointing at the point of interest. This distance is R1. This distance is R2. Maybe I can get this straight. It's pretty close. That's R3. Okay, that one kind of took a dip, but it's supposed to be a straight line. For each one of these little bits, I'm going to erase this. For each one of these little bits of charge or cubes of charge, I get a delta E3. That's from, oh, that's an E1. Delta E1, that's from that delta Q1. I get a delta E2. And, oh man, how do I fit this in? Delta E3. Those are all little vectors. Follow me? So I get a little bit of field from each one. So when I sum over all of those bits of charge, E is approximately equal to K times the sum, just like I did with the point charges, from I equals 1 to N of delta Q sub I over R sub I squared, R sub I hat. That's a lot of notation to tell me add up all the field, okay, and make sure you do it as a vector. Okay. So I can get a decent approximation to the field just by summing it up over all these little cubes of charge. All right? Then we'll do what we always do. E is equal to the limit as delta Q goes to 0 of this thing, okay? Times the integral from I, times the sum from I equals 1 to N of delta Qi divided by Ri squared, Ri hat. That should look familiar to you. This is equivalent to saying the limit as n goes to infinity. I break it up into an infinite number of these little cubes. Okay? Now, you did the same thing in calculus, or in Calc 1 probably, where you want to find the area underneath the curve, and you approximate it with rectangles, and you let delta x go to 0. And as delta x as you take the limit as delta x goes to 0, that's equivalent to taking the limit as the number of little rectangles goes to infinity. And what is that thing that you come out with? The answer for one thing. But this is a Riemann sum, right? So it's the integral. We turn this summation into an integral over the blob. So this is equal to K times the integral. This becomes dq. That's a d. dq over r squared, and my writing is bad. Okay, r squared r hat. That's what we're going to learn how to calculate. dq for us means some little bit of charge, some little tiny infinitesimal bit of charge. For the mathematicians, it means something else. We don't want to worry about that. Okay? So what we're going to do is we'll set up some different charge distributions. We'll figure out how to handle dq for different geometries. We'll decide, okay, what's r squared? What is the distance from that little bit of charge to the point where we want to calculate the electric field? R hat tells us, well, if we're in Cartesian coordinates, which we usually will be, maybe not, we got to take care of the vector. So we're going to find components of the electric field. We'll find the x component, the y component, and so forth. Okay? So we're going to be filling in the blanks. And k is just a constant that's along for the ride. Right? Some different charge distributions. You got a one-dimensional charge distribution, that's a line of charge. Two-dimensional charge distribution, that's a surface of charge. 3 dimensions is like the blob that I drew. It's a sphere of charge, or a blob of charge, or an egg of charge. Okay, something like that. So, for the line of charge, the 1D case, for line charge, imagine that you have a very, very thin line of charge. It has length, let's say in this case, I'm going to do an example shortly, but it has length L, and there's some total charge Q on the line. It's evenly distributed. Doesn't have to be, but I'm saying in this case, we're going to make a simple case where this Q, this total charge, is evenly distributed along this line of length L. The density of charge, lambda, this is the charge density, is Q divided by L. This is some charge per unit length. Charge per unit length. Okay. And this is coulombs per meter. Big Q over capital L. All right. What is dq? That's what we're after. Well, if this is a little bit of length, let me draw this. If this is a little bit of length dl, okay, so I'm breaking it up into little infinitesimal bits of length. dq for a line charge, dq is equal to lambda dl. It's just like any density that you come upon, okay? It's the charge per unit length, you multiply it by a length, and you get the amount of charge. Okay, so dq is lambda dl. That's for a line of charge. You could also have a surface charge. Okay, so let's say you've got some surface, I don't know, looks like this. Here's some little bit of surface area. This is dA. So there's a surface, there's some little, didn't work out too well there. There's a little bit of surface area on that dA. Then dQ, it's the same game. I've got some, if it's uniformly charged, there's some total charge Q divided by the total area, and this is charge divided by area, and that is coulombs per square meter. Okay. And dQ is equal to sigma dA. Sigma is this charge, I'll just put an arrow up there. Sigma is that charge per unit area. Okay. So dQ becomes sigma dA, and you have to figure out somehow how to handle this little bit of dA and do the integral, okay? For a volume charge, like the blob I drew, a sphere of charge, an egg of charge. For a volume charge, so you have some volume, you have some little volume element, okay? It's not too bad. This is dV, okay? Some little bit of volume, like those little cubes. Volume charge is the charge per unit volume, and that is coulombs per cubic meter. And we usually give it the symbol rho. Okay, so rho is the charge per unit volume. That's the way I write rho. Rho, your charge. Okay. So, you guessed it, dQ is equal to rho dV. It's a density times, it's a volume density times some little bit of volume. We probably won't see this one very much, but I will definitely show you the line charge and the surface charge. So, okay. Following me on this, these are just different dimensions of charge distribution. One-dimensional case, line of charge. Two-dimensional, a surface like the surface of this table. And then a three-dimensional like a sphere. Okay. Yes?
So for these dAs and dVs, these aren't the derivatives.
Oh, yeah.
They are.
Oh, yeah.
They are.
I'm just saying for us, okay, this truly means some little bit of volume. Okay? That truly means some little bit of volume. For the mathematicians, it means something else. All right. It means find the Riemann sum, okay, with that being the differential. It's actually, well, you can think of it as an operator, you know. Mathematicians do weird stuff like this. Okay? That doesn't work for us. Right? The integral of 0 is 0, okay? If the integrand is equal to 0, we get 0, not some arbitrary constant. Right? For a mathematician, this says take the antiderivative of 0. Well, that's a constant. For me, this says sum up over all these little bits of dx, and all my little bits of dx are worth 0. That is equal to a constant. That constant is called 0. Okay? All right. So it drives me nuts to see that in a calculus book. But anyway. And I got news for you. When mathematicians come upon something like, when they find something like this, they make it 0 as well. But anyway, okay. And you know, in a lot of texts, they write integral, and physicists do this too, the integral. Okay, that's more mathematical to write it that way because it says this is an operator saying integrate this and let the variable of integration be dx and operate on whatever's over here. Okay, so back to the physics. Let's look at a line of charge, and we'll see how to calculate all this stuff. Okay, so here's the setup. Here's a straight line of charge. Charge is evenly distributed along this line, and it has some charge per unit length lambda. And we're going to be calculating always E is equal to K times the integral of dq divided by r squared r hat. So we're going to fill in the blanks for this thing based on our line of charge. So I'm going to put the origin right here at the center of this line of charge. This has length L, big L. And I want to calculate the electric field at a point up here directly above the origin at a distance A. That's the setup. Okay? So a finite line of charge, uniformly distributed. It has charge per unit length lambda, and I'm some distance A above the center of it. Well, we break it up into little bits of dq. So here's a little bit of dq. Okay. I'm going to let it lie on the x-axis. So this is the x-axis. That's the positive direction of the x-axis. Now, for that little bit of dq, there is a little bit of electric field due to, and I know I drew it a big vector, but okay, there's a little bit of electric field dE due to that little bit of dq. We're going to sum over all those little bits. All right. Well, I know that this lambda is some charge per unit length. I need somehow to integrate over the length of this thing. So dq, I already told you this is equal to lambda dx. That's some little bit of length, and multiply that by lambda, and I get dq. We also need r squared. Well, this distance is r, right? R is always the distance from the charge to the point of interest. That's r. So what is r squared? We're going to be integrating over x, right? We got dx here. You always integrate over wherever the charge lives. Why would you integrate anywhere else? You're always summing over the charge, so it's wherever the charge lives. So what is r squared in terms of a and x? This distance is x, right? Just our arbitrary distance x?
R squared is a squared plus x squared?
Absolutely. So r squared, which we're going to need to do this, is equal to a squared plus x squared. Okay? So we got dq, we've got r squared. We need to take care of r hat. R hat says, well, you can't just add all this up. You got to take into account the vectors. All right. So we're going to need, we're in Cartesian coordinates, we're going to need EX and EY. Okay, I'm not going to put equals. I'm just going to put an arrow or something. Let's deal with, how are we going to deal with these vectors? So there'll be an X component, maybe, and a Y component of the electric field, maybe. One of them better survive. Okay. Well, I know this is I'm going to make a little argument here. You can see if you agree with it. I know for every bit of dq that I have on the right side of the origin, I have the same bit of dq on the left side. Okay? It's symmetric about the origin. So this little bit of dq, let me go up here, gives me a little dE in this direction, right? And just by symmetry, I can see that the X component of the electric field should be 0. Because when you sum over all of this, that X component is always going to cancel out. Whatever X component I get from this side, I'm going to have an equal and opposite X component from the other side. Now, if I were up here, wanting to know what's the field down here at this point, at the end, I couldn't do that. I wouldn't get cancellation. You don't have symmetry about this end. In physics, you're always looking for symmetries to make life easier. Okay? So I claim that EX is 0 by symmetry. Okay, I could prove that. I can do the calculation and I'll get 0, but okay. What about EY? Well, for EY, that's going to survive because these components are going to add to one another, and you're going to get an electric field vector that's in the Y direction. So for that, let me put a line here. Maybe I can fit all this in. We need the component of the electric field, or that little bit of electric field, in the Y direction. So I can call this angle theta. Don't have to. We could call this angle theta. It doesn't matter. That makes this angle, I know you hate it. Erase this stuff. But that makes that angle theta, right? It also makes this angle theta, but okay. So for EY, we need cosine theta, right? That's the Y direction. Need the adjacent component to theta. So for EY, I need cosine theta for that component of E in the Y direction. Well, I'm not integrating over theta. I got to put cosine theta in terms of these variables of integration, which the variable is x. What is cosine theta in terms of these variables?
R
No, cosine theta, not tangent. Here's the triangle. Here's theta. A over R, right? But R, not integrating over R, but I have an expression for R squared. So this is equal to A over x squared plus A squared underneath the radical, right? Can you see that? That's an A. So now I think we have everything that we need. Let's talk about, for a second, let's talk about the limits of integration. Well, you always integrate over the charge. So from minus L over 2 to L over 2, right? Here's another claim by symmetry. I claim that the integral from minus L over 2 to 0, that's going to add up all those components in the y direction, okay? Give me some number. I claim that's exactly equal to the integral from 0 to L over 2. That's just on the other side. So I'm going to integrate from 0 to L over 2. I can prove this to you mathematically. But I'm going to integrate from 0 to L over 2 and double it. You do this all the time when you're, well, all the time. You do it sometimes when you have nice symmetry, when you have even functions, and you're integrating from even intervals, negative and positive. You can just get rid of that left side and integrate from 0 to whatever number you're integrating to and double it, okay? All right, so I think we have everything we need. Let me write down this integral. So EY, okay, got rid of EX, EY is equal to DQ. Well, DQ is lambda dx divided by R squared. R squared is A squared plus X squared. But we also need that component of the vector in the y direction. You don't get all of it. You only get part of it because it's a vector. So I have to multiply by A over the square root of x squared plus, well, let me write it like I did over there. A squared plus x squared, and then we have k, and I don't want to forget to multiply by 2, so I'll squeeze the 2 in over here. And we integrate from 0 to L over 2. So I'll clean that up in a second. Just writing down all the things I figured out. 2k lambda a, all of these are constants, 2k lambda a. So I'll pull those out of the integral, 2k lambda a, and what's left? The integral from 0 to L over 2 of dx over a squared plus x squared to the 3/2 power. Okay. On the test, or when I ask you to do this on your own somewhere, I expect you to be able to get to this. I expect you to be able to figure out what's dq, what's r squared, what component do you need, okay? What are the limits of integration? Now, doing the integral's a mechanical sort of thing. We're, finding the answer, all right? But the physics is in this, setting this up, all right? So you have to do the integral. Well, I did the integral. Let me see. I think it's a trig substitution, or I don't know, a u substitution might work, but I probably looked it up in an integral table. I don't remember, but okay, this is equal to 2k lambda a times x over a squared times the square root of x squared plus a squared. So I'm swapping these. Evaluated from 0 to L over 2. That's what I have. Then I changed them again for some reason. Okay. All right, so one of the a's cancels here. Then you plug in the upper and lower limits. And I'm going to write that over here. So this becomes 2k lambda over a, and this is EY, over a times L over 2 times a squared plus L squared over 4. All that underneath the radical. You can clean that up a little bit more. Multiply top and bottom by 2. And this is 2k lambda over a times L over, what does this become? 4a squared plus L squared. And that's it. Okay. Can you see that? Probably, maybe not back there. I'll rewrite it up here because I want to do a little bit more with it. So EY is equal to 2k lambda over a times L over 4a squared plus L squared. Okay. That's it. That's the electric field at this point, a distance a above the origin. Okay. Are there questions on that? The main thing is, you're going to practice figuring out what dq is, what's r squared, which component you need, all that good stuff. All right, question. What happens to this expression if I let L go to infinity? Does it blow up? Yeah, I'm going to take the limit as L goes to infinity. Why is this useful? Well, oftentimes we do this because you can get a very, very good approximation to the field if you're really, really close to a really, really long wire. So if you have a continuous distribution of charge, very, very long, and you're very close to it, that's a real good approximation. So I want to take the limit as for, this is called an infinite wire or semi-infinite wire. Take the limit as L goes to infinity of 2k lambda over a, and this thing L or a squared plus L squared. What is that equal to? Can somebody just, do we need to call up the ghost of L'Hopital or say a prayer or Google it? I don't know. I'll show you the quick way. Okay. What? You think it blows up? Does it go to 0? Well, 2k lambda over a, that's a constant. We don't have to care about that. L's the only thing going to infinity. So I'm going to divide top and bottom here by L. Is that legal? Yes, it's legal. Okay. Laws of limits, you can do division and multiplication on certain things. Okay. I'm just going to change this expression around a little bit where you can see how the limit works. So if I divide top and bottom by L, I get the limit as L goes to infinity of 2k lambda over a. You get 1 over 4a squared over L squared plus 1. Now what's the limit? Well, nothing happens to the numerator. What happens to the denominator?
It goes to 1.
Goes to 1, yeah. This term goes to 0, right? The limit of 1 as L goes to infinity is 1. Okay? So this whole thing goes to 1 in the limit. And this is equal to 2k lambda over a. This says that for a very, very long wire, as you increase A, the electric field goes to, well, it decreases like 1 over A. Not like 1 over A squared like a point charge would. Okay? Goes like 1 over A. That's going to be an important result for us eventually. Okay. What else can I say about it? What does the field look like due to this line of charge? If you kind of could get a picture of, does this give you any other information about the field, or maybe this? Okay. You have cylindrical symmetry, right? As you go along this very, very long wire, that field is all in that radial direction cylindrically. So it radiates outward in a cylindrical way. You have cylindrical symmetry. Right. If I look at the end of the wire, oops, we're almost out of time. If I look at the end of the wire, take a slice, it looks like a point charge. Right. And it looks that way everywhere along the wire. All those X components have canceled out, and you get something that radiates out like a cylinder. Okay, that's it.